Good morning, everyone. So today we'll have our first talk by David Marsh. So David is visiting from King's College London, and he works in particle physics and cosmology, and he's an expert in axion dark matter. David is also going to be giving two pedagogical lectures. One is tomorrow afternoon, and the other is, I think, on Thursday afternoon on axion stars, axion and ultralight axion dark matter. And I'll hand over to David to start.
Thank you. Yeah, thank you very much for the kind invitation to be here. It's my first time here at ICTS and also my first time in India. So really, really great to be here. Great to see so many friendly faces, be here in person and all of that. So yeah, today I'm going to be doing a research talk about axion explosions. This is work that I've done in 3 papers that came out in quick succession at the beginning of this year. And I think they tell a really nice consistent story about the relationship between particle physics and cosmology. If you haven't come across axions before, some of the ideas here will come quite thick and fast, but hopefully, you know, in the pedagogical talks, you'll catch up on the bits that you don't, that I don't have time to explain in detail here. Okay, so let's get started. Okay, I'm going to have to stand a bit closer. Right, okay, so first of all, axion Lagrangian, what makes something an axion? Well, it's a periodic field. The axion field is phi, has a periodic potential, cosine phi over f. It's also a pseudoscalar, which means it's odd under Cp, so it can couple to operators in the Lagrangian that are also odd under Cp, and this is ff joule of electromagnetism, which is E dot B. So then if you expand the cosine potential for small fluctuations, you get a mass term, quartic self-interactions, and this coupling between axions and photons. For the QCD axion, there is a predicted relationship between the couplings, and we'll talk about that in the second pedagogical lecture. But for an axion-like particle, you can think of all of these parameters as independent, m, lambda, and g. Okay. Now, why are people so excited about axions at the moment? Sort of summarized, and again, we'll talk about this in the pedagogical lecture, by figures like this. So this is constraints on the axion mass versus coupling. And the shaded in regions, the solid regions, are excluded by current measurements. And the QCD axion, sort of the nominal target, this thing over here, this line there. But all the excitement in axion physics at the moment are all the lightly shaded regions, which you can see fill almost all of this parameter space, all the way from constraints from horizontal branch stars, all the way down to constraints from black hole spins. So this is why people are so excited, because this story is going to get completed almost in the next 10 to 20 years. It's a very exciting time to be thinking about axion dark matter. Okay, so what's this talk? We're going to be talking about sort of this region of parameter space, masses around the nano EV, and I'm going to show you some new limits that come down and present the sort of the strongest limits in this region here. Okay, so what's the basic idea behind what I'm going to tell you? So axions can decay via this 2-photon coupling. The perturbative decay, which has a rate like this, g squared m cubed, is very, very long. So for very light fields, this decay rate is very, very small, and axions are effectively stable. However, if you have a dense, coherent environment of dark matter, then a process known as parametric resonance can be triggered, which is just swinging on a swing. And when parametric resonance is triggered, then the decay rate no longer scales like g squared, it only scales like g, and the decay can happen on a cosmologically interesting timescale. Axion stars, which I'll talk about for quite a while, and also in the pedagogical lecture, axion stars provide this dense, coherent dark matter environment where parametric resonance can be triggered. And what I'm going to tell you about in this talk is how we can compute the formation rate and merger rate of these axion stars, which is really a new advancement. People have known about these objects for a long time, but until this work, I don't think anyone could tell you what the formation rate and merger rate of axion stars is. And so I can tell you what the enhanced dark matter decay rate is due to parametric resonance. And finally, if this enhanced decay rate happens in the redshift range 10 to approximately 100 during the dark ages, then the production of photons from axion stars via parametric resonance heats the intergalactic medium, raises the optical depth to the CMB, and if that optical depth becomes too large, I can use that to set new limits on the axion photon interaction strength. So what's the outline to the talk? I'm going to go in detail through these different things. I'm going to tell you about what axion star instabilities are. I'm going to talk about the formation rate of critical axion stars. And I'm going to talk about constraints that come from heating of the intergalactic medium. So let's get started. EM instability of axion stars. So this is work that was done by my grad student, Lena Chung-Jocko. Okay, so boson stars in full general relativity. So this, what I'm going to tell you about now, is done using full numerical relativity with this code called GR-Chombo, which is public, which you can go and download if you want to. So spin zero bosons lead to an oscillating metric on scales, time scales of order the inverse mass, and the formation of compact objects known as oscillotons. And we simulate these things in full three-dimensional numerical relativity, so all the curvature perturbations and all of that, non-curvature perturbations, all the curvature, with the axion interaction potential using GR-Chombo. Okay, so first of all, what happens if I don't have the axion photon couplings, if I only have like that cosine potential? Well, then I can plot the stability of oscillotons, axion stars, as a function of the ADM mass versus the decay constant measured in Planck units. And in the upper part of this plane, when the decay constant is large, the axion stars are stable. If the decay constant is small, but the star is of large mass, then the star will collapse into a black hole. If the decay constant is below a certain point, however, which we call the triple point, then as you increase the mass of the axion star, it's first stable, and then it goes unstable in this, what we called here the dispersion region, or what I call now an axion nova. So the formation of black holes happens above this mass known as the Count mass, and the instability to the axion nova happens above another mass which you can compute, which we'll call the nova mass here. If I add more interactions, if I add the axion photon coupling, then there are more instabilities. For example, the parametric resonance instability to radio emission caused by the axion photon coupling. So now here's a movie of that instability. So on the left-hand side, we've got the axion star. On the right-hand side, we've got the energy density in photons. There's an incoming flux of photons, very small flux of photons needed to trigger the resonance, which is invisible in this plot. Let's have a look. So here's the axion star. It's oscillating. It's an oscillaton. And it's stable. It's stable for quite some time. But then after some time, the parametric resonance instability gets triggered, and you start to produce photons, and there's a lot of very intense photon emission, and then the axion star is gone. Okay. Right, so parametric resonance. So we simulate this compact axion star in a background of incoming electromagnetic wave. The axion field resonantly pumps the electromagnetic field and causes decay of the star. So here's a profile. So this is for a compact axion star, so something close to the Count mass, where strong gravity effects are important. And the energy in the left-hand panel is a function of time. At small couplings, 10 in these units, the star remains stable for a long time. As I increase the coupling to 14, 16, at some point, a decay happens. When the decay happens, there's electromagnetic radiation produced. We can fit the shape of this emission using two parameters, tau and T0, and then tau and T0 here I can plot as a function of the coupling and find that they have an asymptote at a particular critical value of the coupling. And by performing these fits and locating the asymptote, I can work out what the critical value of the coupling or the critical value of the mass is to trigger this instability. And we also know how long the instability takes, and we have fits for that as well. Right, so you need to have an incoming electromagnetic wave which has a frequency of order the inverse size of the oscillaton in order to trigger the resonance. And we checked in the paper that the ambient flux of CMB photons provides enough radiation to trigger that resonance. Yeah, CMB photon can trigger it. There's also some papers by Levkov, Panin and Tkachev, where they show actually that the flux produced by perturbative decay of the axion itself can also trigger the resonance. You only need a very small flux of incoming photons, and then you resonantly pump them. Typically, people say that parametric resonance is something that can be triggered just from quantum fluctuations of the vacuum, because the time scale that this instability happens on is only logarithmically sensitive to the amplitude of the initial field. So even if you just have some quantum fluctuation, you'll eventually pump it up and cause a decay. And it drives the electromagnetic field and causes resonance of the electromagnetic field. So incoming, some photon coming from somewhere, vacuum fluctuation, CMB, doesn't really matter, it's only logarithmically sensitive. Photon comes into the Axion star shakes it and then causes it to be amplified. Okay. Right, so then from doing these fits, we can locate the critical mass and coupling. And by fitting the asymptote of the decay, we work out this plane here in coupling versus mass. And here I've restored physical units, inverse GeV, and solar masses in units of 1/m. And so you see that at small coupling, the star is stable. Small coupling or small mass, the stars are stable. And either large mass or large coupling, the Axion stars are unstable. So now we've got a picture where we've got three different instabilities. You have your soliton, your Axion star, and as you increase it in mass, it can increase to a mass where it decays due to parametric resonance to photons, which may or may not be plasma blocked. I'll talk about that later. The quartic self-interactions can also cause an instability to the Axion nova process, where relativistic axions would be emitted. In the story I'm going to tell you, I'm going to assume couplings that are ordered such that this process happens first. I'm happy to discuss under what assumptions that holds and the consequences of that in the questions. And then as you increase the mass still further, the soliton can collapse to a black hole. The arrows should be the other way around on here, of course. And the Kaup mass, the instability to black holes is always the heaviest of these, as long as you only have Planck suppressed, as long as your operators are, say, Planck suppressed only. Okay, now, second part of the talk, I'm going to talk about the merger and decay rate of Axion stars. So first of all, how do you form Axion stars? So here's a slice through a simulation done by Shive et al., which is a sort of famous first simulations of gravitational collapse, including wave-like effects of dark matter. And they found that in the centers of dark matter halos, you always form these Axion stars in the center. And we'll talk about that in the pedagogical lectures. So now the Axion star abundance. So from these simulations, it was noticed that the Axion stars follow what's called the core halo mass relation, where the mass of the core, the Axion star, is related to the mass of the halo with some particular power, alpha. So if you just assume that there is such a relationship, then you just make a change of variables, and from the halo mass function, you can work out the soliton mass function. And so here that is, I've just taken a standard Schaff-Tolman halo mass function, and I can now tell you how many stars there are, how many Axion stars there are per cubic megaparsec as a function of the Axion star mass, just like the halo mass function. The slope of this relationship is predicted to be 1/3 in virial equilibrium. However, different simulations by different groups and in different cosmological environments have evidence for diversity of the slope between 1/3 and 3/5. We'll talk about this more in a couple of slides' time. If you just take the slope as being fixed, then you can see that the Axion star mass function depends pretty strongly on what the slope of this relationship between the core mass and the halo mass is. So now, how do you grow a critical Axion star? How do you get an Axion star above that critical mass so that it can explode? Well, first of all, if the Axion is light enough, then the parametric resonance decay to photons will be blocked by the plasma mass of the photon. And if the universe has a finite free electron density, so you just know what this plasma mass is, and the plasma mass starts off high and it falls. So if the plasma mass is too large, you just grow critical Axion stars according to this core halo mass relation. Then once the plasma mass drops below twice the Axion mass, the stars are kinematically allowed to explode. And this will give you a burst of at some particular time when this resonance condition is satisfied. Next, you will, if the decay is not plasma blocked, the only way you can form a critical star is by taking two subcritical stars and merging them. So you need to work out the merger rate. And you can also do this in the context of the extended Press-Schechter model from the halo formation rate. And by doing that, I can work out what the soliton major merger rate is at different particular mass scales as a function of redshift. There's the major merger rate evaluated at a given mass scale in the rate per cubic megaparsec as a function of redshift. Okay, so now once you know the merger rate, you can just convert that by reintroducing dimension 4 units, the mass of the critical stars and so on, and work out what the fractional dark matter decay rate is, dF by dz. And we found that our EPS result can be fit with this formula here, and it works very well at axion couplings 10 to the minus 11, 10 to the minus 12 inverse GeV that are not excluded by helioscope measurements. The fit gets bad at large couplings, but these large couplings are excluded by Earth-based experiments. Okay, so you can convert that again if you want to by changing the unit into what's the energy injection from this decay rate of stars. So here's the energy injection in erg per cubic megaparsec per gigayear as a function of redshift for different axion masses, particular coupling, the different solid and dashed lines are for different slopes of the core halo mass relation. But what I want you to notice is that this is about 8 to 10 orders of magnitude larger than the energy injection from POP3 core collapse supernovae for the particular range of parameters that I've chosen. So this is a large energy injection. If you're decaying any significant fraction of the dark matter, it's a heck of a lot of energy. So this makes us this comparison makes us relatively confident that this is an energy injection that should have observable consequences. So now I mentioned the diversity in the core halo mass relation. And this is actually very important and modeling this is what I think one of the really novel aspects of this second piece of work, which was done, sorry, I didn't mention the postdoc who did a lot of this work, which is Xiaolong Du, who's currently at UCLA. Okay, so how do we model the diversity? So this is our model for diversity in the core halo mass relations. This is core mass as a function of halo mass. And the blue slopes are the observed range of diversity in this comparison of a number of simulations done by Chan et al. What we did in this work was we tuned the Monte Carlo parameters of a merger tree, bit of merger tree software called Galacticus by Andrew Benson. And we tuned the parameters of Galacticus to reproduce the observed diversity. So we introduce some cores into our halos, and we change parameters about the way that those masses are initially assigned and about how they can grow through accretion and mergers in order to reproduce this observed diversity. Actually, if you use an original model for how to do this by Xiaolong from 2017, you do not reproduce the observed diversity. So there has to be something going on that wasn't in this model, which assumes only growth from mergers. So the diversity is probably something to do with environmental effects, or historical effects in the formation of a halo. But this model here in the green is a Monte Carlo merger tree model that we tuned to match the observed diversity in simulations. I've just picked a mass range that will turn out to be in the constrained region. So I have to pick a reference mass scale to make plots, but I've just picked one that is in the range of interest. Yeah, if I picked a different particle mass, it would change the scales of the halo mass and core mass, but it wouldn't change the statistics. Yeah. Okay, right. So I'll show you the constraints in a few slides' time. At this mass, the QCD axion is too weakly coupled to be constrained by this process. So the constraints I'm going to get are going to be above the QCD line. But the QCD axion at this mass, 10 to the minus 11 eV, is in the search range of this dark matter detection program called DM Radio. It corresponds to axion decay constants for the QCD axion of around the Guth scale. Yeah. Yes, yeah, the star size is roughly in the compact limit, the star size is the Compton wavelength. In the non-compact limit, in the non-compact limit, in virial equilibrium, which is this 1/3 slope, then the size of the star is in equilibrium with the de Broglie wavelength in the halo. We'll talk about that more in the pedagogical lecture. Okay, so by using this Monte Carlo model for axion star, for diversity in the slope relationship between core mass and halo mass, we can also fit. So here the squares and the stars are the Monte Carlo models, and the solid lines are the EPS extended Press-Schechter results with different values of the slope parameter. And in the case of the diversity Monte Carlo model, which is the squares, it's well fit by the EPS model with a slope of 2/5. And so you can sort of think why that would be the case. Basically, these things average out and have some effective average slope. And in order to make the fractional dark matter decay rate, I'm averaging out in this direction. So that makes sense. And our model that reflects the diversity observed in simulations is effectively a slope of 2/5. Right, so now on to part 3 of the talk, the last part of the talk. I'm going to talk about how these axion star explosions heat the intergalactic medium. And this is work done largely by postdoc Miguel Escudero and their grad student, Karis Pooney. So a reminder of the cosmic timeline. Tom in his pedagogical lecture is going to talk about the formation of the first stars. So I think you'll get more about this. So we start off in the Big Bang, we have the radiation era, then the universe becomes effectively neutral and the CMB propagates its photons to us. And then while the universe is effectively neutral while dark matter structure formation happens, and then once structure formation passes the baryon gene scale and baryons collapse into halos and that ignites star formation, then the first stars reionize the universe at a redshift of around 6 or 10. The dark ages end, and then we have galaxies. And the physics that I'm interested in here is physics before the reionization epoch. So during this dark ages period when there are no stars around to heat the intergalactic medium. And the observable I'm going to use to place constraints on heating of the intergalactic medium is the CMB optical depth. I'm a CMB cosmologist by training, so I have to tell you a little bit about the CMB. So here is the large scale polarization spectrum of the CMB, the EE polarization, 2-point correlation function thereof in microkelvin squared as a function of multipole L. And the large scale polarization, so this bit here at low L, which I've got a zoom in of in this panel up here, the low L polarization at scales like the square of the optical depth, the optical depth for photons going through the ionized plasma at late times. So here is the EE spectrum at low multipoles, and the colors are different values of the optical depth tau. As the optical depth tau increases, the amplitude of polarization increases. And that's because what creates CMB polarization is the Compton scattering of CMB photons off the charge density of electrons. So that's why the spectrum has acoustic features at large L. Acoustic features are caused by the scattering of CMB photons at the surface of last scattering when the universe just became neutral. That creates the acoustic features. And then the bump that we see here is the reionization, is what we call the reionization bump caused by the late universe. And so the Planck satellite makes a good measurement of the amplitude of the polarization spectrum at low L. And so we can reconstruct the free electron fraction, XE, or the optical depth tau. The optical depth tau is measured by Planck to be around 0.054, 0.06. And the reconstruction of the free electron fraction, XE, as a function of redshift, looks something like this. So the CMB is consistent with reionization happening somewhere around 10. There are, of course, systematics and things to talk about here, and they're gone into in depth in these Planck papers. So decaying dark matter, which is what really these axion star explosions are, I expressed it as a fractional dark matter decay rate F, increases tau. But even a small fraction, around 2 times 10 to the minus 9 of the dark matter, if you decay just 2 times 10 to the minus 9 of the dark matter in the late universe, it's enough energy to reionize the universe. And that's 2 times 10 to the minus 9 might sound like a small number, but think the baryons are much less than the dark matter, the stars are much less than the baryons, and the stars don't put all of their energy into reionizing the universe. Even a smaller fraction than 2 times 10 to the minus 9 can provide enough energy, maybe not to reionize the universe, but to increase tau some amount above that 0.06 and lead to exclusions. This story of decaying dark matter and the CMB optical depth leads to well-known limits on heavy WIMP-like dark matter decaying at late times, worked by Tracy Slatyer and collaborators. Now, axion star explosions give an enhanced axion decay rate. This thing I've been computing DFDZ, the F being the fraction of dark matter and per redshift. So here's a sketch of that. So this is sort of the total decaying dark matter fraction in these models. Now as a function of axion mass at low masses compared to the redshift when the decay happens if you're plasma blocked, and for different values of the coupling. And so you see that for at particular redshifts and for particular masses, there is enough dark matter decaying to reionize the universe. So here in reference 10 to the minus 11, 10 to the minus 12 inverse GeV couplings and particular masses, you will have enough energy to reionize the universe. So here's another nice cartoon by Karas, sort of so you can envision what's going on here. So we have our critical solitons hanging around. We can work out the energy density in the critical solitons and the merger rate of critical solitons using this extended Perceptor or merger tree stuff. Then when you create your merge to almost critical solitons, you will emit energy into the IgM. And you have some very low energy photon, it's absorbed and creates heat in the plasma, or rather creates heat in the neutral hydrogen. And when we have different possible signatures, if you're blocked and you have this big burst of axion stars all exploding at the same time, it turns out you have patchy reionization. Whereas if you have these mergers that are happening sort of continuously all over the place, then you have a more smooth reionization history. So we modeling this energy injection are able to give models for the possible reionization history in addition to lambda CDM caused by this model. So here's the free electron fraction as on a log scale as a function of redshift. The black is lambda CDM, and then the additional effects caused by axion star decay. We don't include ordinary reionization in this model, are shown by the colored models. So basically, any of these models where you've got significant extra, free electron fraction at redshift of like 20 or 30, would be inconsistent with the observations of the CMB if we've got huge amounts of extra free electrons. And then here's the IgM temperature, the temperature of the baryons as a function of redshifts for similar models. The symbols are marked on the next panel where they are in the parameter space. So these are the constraints on axion parameter space that you end up with. So the solid regions are excluded by our analysis. And so here we've got the axion mass and the axion photon coupling. The axion helioscope casts, say, an axion solar telescope, excludes couplings around 10 to the minus 10 inverse GeV. The X-ray spectrum oscillations, Fermi gamma rays, and so on, constrain couplings around 10 to the minus 12 inverse GeV, but they drop off as you go to higher mass. The QCD axion is not visible on this plot; it would be sort of off down here somewhere. And then our limits from the axion star explosions, exclude the solid region here. So our new limit, so we set new limits in the range around 10 to the minus 12 to 10 to the minus 8 EV for the axion mass, which can be up to 2 orders of magnitude stronger than the existing astrophysical constraints. There is an important difference between these types of limits and the ones we have. The CAST and the X-ray gamma ray limits do not assume that the axion is all of the dark matter, whereas our limits apply if the axion is all of the dark matter. So our limits are more comparable to a direct detection search or an indirect dark matter detection limit, where the limits depend on you being all of the dark matter. If I set a limit with, let's say, xenon searching for WIMPs, the limit applies assuming the WIMP is all of the dark matter. If I set a limit on axions using ADMX axion haloscope, the limit applies assuming that you're all of the dark matter. This limit applies assuming that you're all of the dark matter. And then we also get another sort of smaller limit at around 10 to the minus 13 EV, and this is caused by the burst case, whereas this is caused by the mergers case without plasma blocking. And then we did some very, very approximate estimates for how well you might be able to improve this with 21 centimeter, really just based on energetics arguments. And the strongest of these is just saying, well, very, very roughly, you might assume that 21 centimeter could tell if you have something that increases the IgM temperature to be more than the photon temperature. So the 21 centimeter ones are very, very approximate, but they are interesting because there is a new dark matter search called DM Radio, being built by some of Tom's collaborators at Stanford. And DM Radio is aiming to search for the QCD axion here. Well, search for axion dark matter here, and eventually ramp up their search in sensitivity to reach the QCD axion down here. Now, while DM Radio are doing all of their preliminary searches, they will be searching in this region of parameter space. So if DM Radio goes away and finds something here from the axion star explosions that we're looking at, there should be a signal that goes along with it in 21 centimeter. Alternatively, if they find something here, then there is something different about the model than the assumptions that I've put in into my model. So I think that this is very important. Our model is relatively rough, and it invites a lot more exploration, particularly of axion star explosions in 21 centimeter. Okay, so I'm roughly at 35 minutes by my timer, so I will wrap up and summarize. So axion stars explode into radio photons above a critical mass, and we can show this in full nonlinear general relativity simulations. We can also compute the formation rate of axion stars due to major mergers using well-known tools to cosmologists of extended pressure theory and merger trees. And from this, we can compute the dark matter decay rate induced by these axion star explosions. And then finally, these axion star explosions lead to ionization and heating of the intergalactic medium, and they set new powerful limits on axion dark matter and open up new ways to search for it using 21 centimeter. So thank you very much.
Questions? Shubina.
So the axion stars can be entire dark matter. I'm little because you said that it can decay and then only 0.06.
So the assumption here is that the axions are all of the dark matter, but I compute the fraction that's in axion stars using extended pressure. So the axion stars are only a tiny fraction of the dark matter, which would be smaller, which would be around, it would be around the sort of 10 to the minus 9 scale.
So the other dark matter comes from the fuzzy area.
Just comes from the rest of the
Rest
axions.
of the axion. Okay.
Just the rest. So we'll go into axion cosmology and the details of the relationship between an axion star and its halo and the formation mechanisms in the pedagogical lecture. But yeah, the rest of the dark matter would be the ambient axion field, which is not coherent.
So for the 21 centimeters search, does it matter whether, again, you have patchy reionization? Like, are you considering only the global signal, or are you looking at?
So in order to do this very approximate sort of reach forecast, we've only looked at the IGM at the temperature. At the back, we only looked at the baryon temperature and looked at when it departs enough that we think you might be able to say it in 21 centimeter. I think that what you would have to do to really model this, the effect on 21 centimeter, is take something like 21 centimeter fast, input into that some of the physics that we put into the merger trees about when the stars go critical, and put that energy injection in, and then you get patchy reionization. There's also an interesting question that in order to compute this decay rate and possibility of plasma blocking and so on, we assume that the baryon temperature is uniform, and we thought, well, that's okay, because the masses of the halos where this is taking place are well below the baryon gene scale. However, you might still be affected by inhomogeneities in the baryon temperature, and that is not included in this analysis, and would be an important step in using, as I said, 21 centimeter fast to do this properly.
Okay, so I had a question regarding the radio photons emitted when Exion stars exploded.
Yeah.
So my question is, how would that be different from other radio photon signatures? Like, how would you differentiate between the signals from an Exion star explosion and from other signatures?
Right. Yeah. So that's a good question. The axions, the photons that you get from the axion star explosion are very low frequency. So axion masses here, 10 to the minus 11 eV. Oh, what's that? That's about a kilohertz or so, I think, or a few kilohertz. So it's very low energy radio photons. So you're not thinking of observing these radio photons directly. And as far as this analysis is concerned, all they have to do is heat the IGM. So anything that heats the IGM, like looks the same as far as CMB optical depth is concerned. And so what we're doing here is we're really just saying, well, if you increase if there's enough energy to increase the optical depth above its observed value, that model is excluded regardless of what it is. If you had a model of, say, AGN or of supernova formation I talked about that creates too much energy and says tau is 0.1 instead of 0.06, then that model would be excluded. So here we're not thinking of doing a search, we're only thinking of setting a limit.
In one of the slides, the Schiff paper, there they have done the simulations using the Schrödinger-Poisson system. So that doesn't take into account self-interactions of any sort, right? Especially if it's axions, it will have some self-coupling.
Yes. Right. Yeah. So this will come up in one of the pedagogical lectures. Yeah, the simulations, the Chivay simulations that I showed that have this axion star formation, they solve what's called the Schrödinger-Poisson equation, which is a non-relativistic limit of the Klein-Gordon equation, and you find the formation of these axion stars. They don't have any. They're in perturbation theory in terms of the metric. They don't have self-interactions. They don't have quartic self-interactions. My limits here assume the quartic interactions are subdominant to the axion photon coupling, which again, I'm happy to discuss probably over coffee. And the axion photon coupling is not included in the Chivay stuff at all because it's entirely non-relativistic. So if you wanted to include, so the input that we use from the Chivay and Chivay-like simulations, this compilation by Chan et al., is really the relationship between, which is modeled here in terms of the slope parameter, and the relationship between the halo mass and its corresponding axion star. That's the only information we use from those simulations.
Thank you.
Other question? Yeah.
Hi, this is Himanshu. Thanks for the wonderful talk. My question is regarding the enhancement of axion decay into photons because of the high density of axion stars.
Yeah.
So don't you think that when the axions will collapse into axion stars and the size is very small, so even if you have initial angular momentum in that axion cloud, a very small spinning, small axion star will be very spinning kind of right? And that
Mm.
would basically reduce the density effectively, and hence bounds
So-
may get affected.
As far as I know, it's a very interesting question. As far as I know, the Axion stars don't have any spin. And that's because there are grounds, and I don't think they can have any spin, because they're the ground state of a scalar. So this, particularly the coherent configuration that I'm calling an Axion star, sometimes called an oscillaton, sometimes called a soliton, so soliton in the non-relativistic limit, is a coherent configuration of a scalar. So I don't think it can have any angular momentum.
I see.
But something related to your question is, in order to have a resonance happen, the star has to be of the right size, such that as a photon goes through it, it can have multiple interactions and get resonantly excited. So there is the resonant condition that we found here, and that was known in perturbation theory from a number of papers before, essentially since the 1980s, and Igor Tkachev. The resonance condition here can be expressed as a relationship between the size of the star and the wavelength of the photon. So the star size plays an important role. I don't know anything about angular momentum, but it's an interesting question. I'll look into it.
Hi, David.
Hello.
Hi, Vasudev here. So first of all, nice talk. I had a question about the CMB optical depth.
Yeah.
So let us assume that we are having an inhomogeneous distributions of axion stars in the sky.
Mhm.
So in one patch, you are basically having more axion stars than in the other region.
Yeah.
So how will the CMB characteristics change? Like, will the temperature map of the CMB change somehow?
Right. Okay. So yeah, good question. So in the two different regions of excluded parameter space, one of those regions, we think that the reionization will be essentially homogeneous. In the other region, we think the reionization will be only patchy. Where reionization is patchy, we introduce a fudge factor for how that affects the optical depth. But patchy reionization can show up in other ways in the CMB. One way in which patchy reionization shows up in the CMB, which in order to model properly would be sort of related to my question about 21 centimeter, is called the kinetic Sunyaev-Zeldovich effect. So if you have lumps where the free electron density is not distributed evenly, this happens in clusters at late times, but it can happen at early times during reionization. Then the relative velocity between the baryons in those clumps and the CMB rest frame, I think I'm explaining KSC correctly here, introduces something called the kinetic Sunyaev-Zeldovich effect, which introduces extra anisotropies into the CMB. So extra anisotropies introduces extra power sort of over here at L of about 10 to the 4, corresponding to the angular size of the lumps. So patchy reionization can introduce small angle extra anisotropies in the CMB, in the KSC effect.
What about large scale?
Large scale, you wouldn't expect any correlation on large scale, because apart from this, so the only correlation on large scale is from the overall integrated optical depth. You wouldn't expect, any correlation between an axion star exploding over here and one exploding over here. So you wouldn't expect anything else large scale.
Thank you.
I have a question on.
So maybe we're at 40 minutes. We can take the questions to discussion.
Okay.
So thanks a lot, David.
So much.
And let's thank